Today's lecture is on the first part of the properties of the DTFT. The goal of this lecture is to cover properties of the DTFT, including periodicity, linearity, time and frequency shift, time reversal, conjugation, first difference, and accumulator. And we will also give some examples for a few of these properties. The first property, which you know by now, which is the fact that the DTFT is periodic in omega and has period 2 pi. So we proved this in the previous lecture. So and more formally, this means that x of ej omega plus 2 pi is equal to x of ej omega. The second property you are also familiar with, and it says that the DTFT is actually a linear transformation, meaning that the transform of the sum or the weighted sum is the sum of the transform. So we usually use this property a lot even without thinking about it. Now we get to the time and frequency shift, and the first property, which is the time shift, it says that the DTFT of the shifted version of x by n0 is equal to e minus j omega n0 x of eg omega. So a shift in the time domain results in a multiplication by e minus j omega n0. So n0 is the how much I shifted the original signal times the Fourier transform or the DTFT. So to give you an example, let's suppose that x of n is equal to 1/2 to the power n u of n. Then you know that x of ej omega based on, we did this problem last time. You can just use the geometric series formula, so it's 1/1 minus 1/2 e minus j omega. And this means that if I shift, so the signal here looks something like this. It's the discrete version of this, right? So as if I shift it by, let's say, 2, so if I call y of n is xn minus 2, this means that it's 1/2 n minus 2 un minus 2. So it starts at 2 here. So this is yn. Then y of ej omega, I can say that it is, by applying the formula, equal e minus j 2 omega divided by 1 minus 1/2 e minus j omega. So if you remember the formula also that we studied, the property, the same property that we studied for the Z transformer, so it's the same thing. And there's some kind of duality here in terms of doing the shift in the frequency domain correspond to multiplying by ej omega 0 and in the time domain. Again, omega 0 is the shift that I apply to the DTFT in the frequency domain, so I have to multiply by ej omega 0 and in the time domain. Now, I won't do the proofs here, but the proofs just follow immediately from the definitions. Another property also that follows immediately from the definitions that is time reversal. So f of x minus n is x of e minus j omega. So if I want to keep the same example as before, so x of n equal 1n 1/2 to the power n u of n. Then if y of n equal to 1/2 to the power minus n u minus n. So if this signal, if x of n looks something like this, this is x of n, then y of n is reversed, so I'm gonna draw it in blue here, so it's gonna be this symmetric part of it, so this is y of n. And then you can obtain y of ej omega is equal to x of e minus j omega, which is in this case 1 divided by 1 minus 1/2 So you just have to replace omega by minus omega. So here we get ej omega. So usually, I mean, if you can see this property while working out the problem is good, you can replace it. But usually you can do it. You can easily obtain it by just applying the formula, so you don't have to remember it. This will also give you the property that if x of n is even, meaning that x of n is equal to x of minus n, meaning it's symmetric with respect to the y-axis, meaning something like this. Oh. I think we did an example, or I asked you to do an example where x of n was equal to half to the power absolute value of n. So that's an even signal. And in this case also the DTFT is even. And if the signal is odd, then also the DTFT is odd. And this follows from the time reversal property. The next property we're going to talk about is the conjugation, and the property says that the DTFT of the conjugate of xn, which is x star n, is the conjugate of the DTFT but evaluated at e minus j omega, meaning you have to take the conjugate of the function and you have to replace omega by minus omega. If you remember, we did the same thing for the z transform. If you remember, in the z transform, if we had the if y of n is equal to x star of n, the conjugate of n, then y of z has to be equal to x star evaluated at z star. But here z is equal to ej omega. This means that z star is e minus j omega. So this is just to tell you that if you just wanted some connection to the z transform to justify whether this is true, you could also check this is true by doing the definition. Now, if x of n is real, this means that x of n is equal to x star of n, it's equal to its conjugate, and this means that x of ej omega is equal to x star of e minus j omega, because so this part is the DTFT of this part, and this part is the DTFT of this part. This means that, so what does that mean? This means that if x of n is real, and if I take the norm on both sides here, so if I take the norm here and the norm here, or the amplitude or the magnitude here, then this means that the magnitude of x of ej omega is equal to the magnitude of x of e minus j omega. And this means that if I draw the magnitude here, then it has to be symmetric around the x-axis, around the y-axis, right? Now the first difference, this is similar a little bit to derivation, but since the signal is discrete, so this is kind of the equivalence, the equivalent notion of taking the derivative with respect to a discrete signal. So x of n minus xn minus 1, so the DTFT is going to be the DTFT of x of n, which is xe j omega, minus the DTFT of the shifted version, which is going to be minus e minus j omega xe of j omega. So this can be easily shown using linearity and time shift. The accumulator property of a signal is very similar to the integral, but it's the discrete version of the integral. So here y of n, which is the accumulator, is defined as the sum from m equal to minus infinity to n of x of m. So it's like I'm integrating from minus infinity to m. And the DTFT of y is 1 over 1 minus ej omega x of ej omega plus pi x ej 0, meaning I'm evaluating x, the DTFT at 0, plus a train of impulses. So now I don't want to prove it, give a full proof of it, but I just want to do a sketch of the proof. You can find the full proof in the book. So basically, the main so this part is easy, because if yn has this formula, then xn, I can write xn as yn minus yn minus 1, right? Which means that if yn is the integral, then xn is the derivative, meaning xm is the first difference, which we did on the previous slide. This means that from the previous from the first difference, so we know from previous slide that this means that x of ej omega is equal to 1 minus e minus j omega y of ej omega. And this what gives me this part here. Now this part here is maybe a little bit puzzling, but this is kind of when you integrate, this is like the constant. And why you need this? Because it's true that x of n equal 1, y of n minus y of n minus 1, but also it's true for any constant. So if you add any constant to y of n, it's also true. So if I add here any constant signal c, so plus c and plus c, this is also true. So I need to account for this constant here, and this is how I get this term, this part of the term. So any constant here, any constant c is actually an impulse train, right? And when you do the DTFT of it, this is going to give you an impulse train also in the Fourier domain or in the frequency domain. That was the exercise at the end of the previous lecture. And so an impulse train in the time domain of period capital N gives you an impulse train in the Fourier domain with period 2 pi by n, and here n is equal to 1, so this is why you get the period is 2 pi. But so again, this is kind of a very high level sketch of the proof. So this, you can interpret this as the constant of the integration and try to give a little bit of motivation why. Because it's like in, again, it's like in when you integrate and you do the derivative. If you do the derivative, if you add any constant, it's not going to matter to the derivative. It's like here, that what I did here. But you need to account for that constant here. And this reflects the DC level or average value that for this signal. So let's use the accumulator value to find the DTFT of the unit step function, which is x of n is equal to u of n. Recall that in the first lecture, at the end of it, I asked you to prove that the step function is neither summable nor square summable. But still, it does have a DTFT, and that's what we're going to do today. We're going to try to find the DTFT of u of n using the accumulator function. So the key observation here is to write the step function as the accumulator function of the impulse function here. So because I don't know if you can see it, but u of n is equal to, so you're summing these deltas, right? It's sum from m equal to 0 to infinity delta n minus m, right? And now I can do a change of variable here. So I'm gonna call this guy L, and this is the summation. So m equal to 0 corresponds to L equal to n, and m equal to infinity corresponds to L equal minus infinity. So this is gonna equal L equal minus infinity to again, for m equal to 0, L equal to n delta L, which is exactly this. So basically the step function, the main takeaway message here is that the step function is the accumulator of the impulse, or it's the integral of the impulse function. So if x of n is equal to my signal, which is the step function, so this means that by definition, and I'm calling g of n delta of n just to be able to write capital G of e j omega here. So then I can use the formula of the accumulator function. I know that we also did this in the first lecture. So for g of n equal to delta of n, then g of ej omega is equal to 1, if you remember. So now when I apply the accumulator function to here, so I get that the DTFT of the step function is equal 1 divided by 1 minus ej omega capital G of ej omega plus the DC level here, pi j ej 0 sum of the, and here you have the train function, the train impulse function, and then we know that the DTFT of the impulse is 1, so it's going to be 1 divided by 1 minus e minus j omega plus pi sum from L equals minus infinity to plus infinity delta omega minus 2 pi L. And this is the DTFT of the step function. So it's 1 over 1 minus e minus j omega plus pi times an impulse train function. This brings me to the end of this lecture with a problem for you to try by yourself, which is to find the impulse response of the high pass filter depicted below. So if you remember, we did before the low pass filter. So for the low pass filter, we already found the DTFT of it. So the low pass filter was something like this, so minus lambda and plus lambda. And of course you have the replication here because it's periodic. And we found, if you remember, we found the DTFT of it, or the impulse response of this filter, and it was something that looked like the sinc function. So here the question is to find the impulse response of the high pass filter. You can see that this guy here is a shifted version of this guy here, right? So what I want you to do is that to apply the shift so it's shifted in frequencies, so to apply the frequency shift formula and use the result from the previous lecture to find the impulse response of a high pass filter.